Well, we've paid our dues with the limit definition of the derivative for long enough. Let's start to develop some rules of differentiation so we don't have to keep running through this limit as h goes to 0 process again and again and again as we take derivatives. There are many of these so-called rules that we'll develop here for derivatives. The good news is it'll make the derivatives a lot easier. The somewhat bad news is then we can take the derivatives of far more complicated functions. So we're not really getting away with anything because we'll just make the functions more and more complicated and then apply these rules. But so far we've been fairly limited on what we can really approach with derivatives. A couple of polynomials, a couple of rational functions, maybe a square root here and there. But let's work up these rules and see where that gets us. Okay, first off we have the constant rule, which tells us that d by dx of some constant c is 0, or the derivative of some constant c is 0. You can think of a constant c like a function y equals c, right? So think of this as like y equals 5 or something like that. If we were to graph that function, something like this, right, and then we just graph it, there we go, it would be a nice horizontal line. Well, what's the slope of the tangent line for any point on a horizontal line? It's always 0. The slope of the tangent line to a horizontal line is always going to be 0. Thus, the derivative of any constant, well, that's just the slope of the tangent line, so of course that is also going to be 0. So that's a good start. Next we have the power rule. The power rule is pure gold when it comes to efficiency of calculating derivatives. It tells us that d by dx of x to the n is equal to n times x to the n minus 1. And this really changes everything here. So let's look at what's happening here. This n in the exponent is coming down. It basically comes down to the front, and then you subtract 1 from that exponent. Now, rather than proving this, there is a proof in the book for n being an integer, at least. I'll just give a couple of cases just to kind of back it up and really build some appreciation for this, right? So let's just try it out for the x squared case. Well, if we didn't know the power rule, we'd have to do it by hand, so let's just do that one more time for old time's sake before we abandon this limit method altogether. Right, it's what, f of x plus h, so that gives us x plus h squared minus f of x, so there's x squared all over h. Okay, well, let's expand this out, right? We've done this enough times now. X squared plus 2xh plus h squared minus x squared all over h. And of course we still have the limit here, as h goes to 0. X squareds cancel, and that gives us the limit as h goes to 0 of, what do we have, 2xh plus h squared. So I'm just going to factor an h out of the top here. 2x plus h all over h. Those h's cancel. Now we can finally evaluate the limit. We plug in 0 for h, and we get 2x. Voila. Well, that's the same thing if we would have just taken this 2 down and subtracted 1. We'd get 2x to the 2 minus 1. Well, that's 2x to the 1, which is 2x. Same thing. And so I think I mentioned when we were first developing these limits that we'll get a method one of these days that will allow us to do this whole thing in literally seconds, if not a second even. Well, here we are. We've arrived. Let's try it one more time with x to the third, just for a proof of concept. So this is kind of hand wavy. It's not really mathematically sound to just say, let's try it for a few cases, but it does help to drill home the point here. Okay, let's just see if it works. Limit as h goes to 0 of x plus h cubed minus x cubed all over h. Well, maybe you know the formula for x plus h cubed, maybe you don't. If you don't, you could just write this as, three binomials side by side and FOIL 2 and then distribute the remainder. I like to use this formula though. A plus b cubed this comes from the binomial theorem technically, but I find it useful to actually know this formula. Even in calculus, it actually pays dividends because it shows up enough that it's worth it to memorize. So here we go. A plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. That is the expansion of a binomial cubed. So look what's happening here. You start with all a and you end with all b. And then as we go from left to right, the a's go down. So we have a cubed, a squared, a to the first, a to the 0. And the b's go up. We start with b to the 0, b to the first, b squared, b cubed. Right, so that's an easy way to remember. And then you have 3's here in the middle. That's a different story. You essentially have to memorize those. Though you can use like Pascal's triangle or the binomial theorem if you really want to dig deep on this. Point is, we can expand this binomial cubed in this limit. Okay, so we have the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Now, aren't you glad we don't have to keep doing this anymore now that we have this formula? But again, we're just paying our dues. Let's do it one last time here. Okay, limit as h goes to 0. Let's see what we can make happen here. Well, the x cubes cancel. We have x cubed and then minus x cubed. But then we can factor an h out of everything remaining. So we have, if we factor an h out, we have 3x squared plus 3xh plus h squared all over h. And now finally we can cancel that h out. And now we can evaluate the limit because there's nothing left in the denominator. Everything's good to go for this limit. When we do that, the terms with the h in them will go to 0, leaving us with 3x squared. Whew, that was a lot of work. If we do it using the power rule, look what happens. So I'm going back over here to our original derivative. Okay, we'll bring the 3 down and subtract 1. 3x to the power of 3 minus 1. Well, that is simply 3x squared. Wow, that was fast. So the power rule, it really changes everything. I would say this initiates an entire new phase in calculus. Now that we have the power rule, we take off in a completely new direction. We kind of start leaving the limits behind a little bit, at least for now, and start doing some very serious calculations, which is kind of nice. Sometimes it's fun to just calculate some things. One last thing about the power rule that I'll say, this right here for today, well, okay, so which ends does this apply to? Is it the integers in? So this tells us that n lives in z. This is a double z type situation. This is the integers. And the proof in this section is for the integers. So yes, it holds for integers. So it holds for both positive and negative numbers. But it turns out it actually holds for all real numbers. So we would say n is in the real numbers. This epsilon thing here means is in the set of. And that's something addressed in a future section in Calc 1 though. So the way I like to think of it is like, hey, let's just go with it as n being in the real numbers. We might as well internalize it that way since that's the way it actually is mathematically. So this works for any n in the real numbers. I guess, let's be careful. It wouldn't work for 0, right? Because then we'd be in a constant situation. So we do have to be a little careful. But other than that, it works for any n in the real numbers. Okay, so that's the power rule. Moving on, we have the constant multiple rule. The constant multiple rule tells us that d by dx of a constant times the function, c times f of x, equals the constant times d by dx of the function. So what this really means is that a constant comes out of the derivative, pops out to the front, and there it is in the front. And that's another one that's just pure gold when it comes down to doing larger calculations with derivatives. Well, let's do a proof of this. We can prove this fairly quickly. Let's do d by dx of a constant times f of x. All right, well, okay, back to our limit definition of the derivative. We never quite leave this entirely. That would just give us c f of x plus h minus f of x all over h. Minus c f of x all over h. Well, this constant can just get factored out of the front, and because of our properties of limits, it could even get factored out to the front of the limit. So we have the c times the constant comes all the way out to the front of that limit. Limit as h goes to 0, all the same stuff, f of x plus h minus f of x all over h. But now we're just back to the derivative. This thing left here is just the derivative, f prime of x. So then this must equal c times d by dx of f of x. And we have shown that the constant goes from inside the derivative to out in the front of the derivative. Again, super useful as we go forward with these calculations. Okay, lastly for now, we have one more differentiation rule, and that's known as the sum rule. So the sum rule is pretty much what we'd expect it to be, given its name. It just says the derivative, d by dx, of the sum of functions, f of x plus g of x, is the sum of the derivatives. So that equals d by dx of f of x plus d by dx of g of x. And note that this would also work for minus, right? That's just a result of the constant multiple rule with a minus 1. So this would also work for minus if we include -1 for a constant c. Same thing holds. I won't prove this one, but we can imagine that the proof is very straightforward, right? We just hit it with the limit definition of the derivative. Then we use those properties of limits to separate out this sum inside the limit into two separate limits, and voila, we get a proof like that. So here we have a good start on our rules of differentiation. We have a constant rule, the power rule, the constant multiple rule, and the sum rule. And that's a lot, right? But what are we missing still? Well, we don't have anything about products yet. So we are missing d by dx of f times g. We don't have anything about derivative or division yet. D by dx of f divided by g is still missing. We've said something about x to the n, but what about the derivative d by dx of some, we'll call it just some base b to the x? We don't have anything about that yet, so that's still missing. Well, we could even go from there. We haven't said anything about trig, natural log of x, etc. So while we have these rules, we're still going to need to develop some more rules and some general derivatives for the trig and natural log to get all of our derivatives. But this is certainly progress, and then the rules for the rest of these will come soon.